Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on January 23, 2026, just 1 week ago. It proposes a surprising method to predict how well a model is doing using a single gradient calculation, allowing for checkpoint selection that comes within roughly 1% of the optimal choice without ever needing a validation set. The paper is titled, "No Validation, No Problem, Predicting Model Performance from a Single Gradient." And as we'll see in the results, the consistency of this metric across different model architectures is quite significant. Well, Figure 2 quantifies this precision by plotting the selector gap across various architectures. The vertical axis tracks the difference in top one accuracy between the true best checkpoint and the one chosen by minimizing the gradient norm. Remarkably, for models like EfficientNet B0, VIT small, and ConvNex tiny, the gap sits right at 0, meaning the method identified the optimal checkpoint perfectly. Even where it misses, the performance drop remains negligible, staying under 0.03. So, to understand the mechanism behind that success, Figure 1 visualizes the raw correlation for 7 different architectures. Each panel plots top one accuracy against the head gradient norm, showing a consistent downward trend. In the top left, the plot for ResNet 50 shows a strong negative correlation of about 0.75. This relationship is even tighter for transformers. The middle panel for VIT base, for instance, reveals a correlation of nearly negative 0.9, confirming that a smaller gradient norm reliably predicts better performance. Alright, Figure 3 benchmarks this gradient method against a common alternative, simple model confidence. The top panel plots the correlation with top one accuracy for 7 different models. Notice the blue bars, representing the gradient norm. They extend deeply downwards, indicating a very strong negative correlation, often exceeding 0.8 in magnitude. Compare this to the orange bars for confidence. While they are positive, they are much shorter, meaning the relationship is weaker. The bottom panel confirms this trend for loss prediction, where the gradient norm again provides a significantly stronger signal than confidence across the board. Well, having established the trend for image classification, Figure 4 explores whether it holds for object detection. This plot maps mean average precision against the classification head gradient norm for 6 different CNN detectors. The negative correlation persists strongly as high-performing models like FCOS and RetinaNet cluster in the top left with small gradients. Conversely, lighter models like SSD Lite drift to the bottom right with much larger norms. The yellow box confirms this with a Pearson correlation of negative 0.814, showing the proxy is robust across tasks. So, Table 1 contrasts the method's precision within a single model family against its general performance across diverse architectures. Looking at the first row, specifically for the ResNet 5 family, the authors use a weight-normalized metric called score W. This yields an extremely high Pearson correlation of negative 0.97, which is impressive. The second row then averages across all 25 models using the feature normalized score Z. Even with this diversity, the correlation stays strong at negative 0.85, confirming the method works broadly while peaking with family-specific tuning. Okay, shifting focus to instance segmentation, Figure 6 proves the signal remains reliable for mask tasks. The first panel plots mask average precision against the gradient norm for families like mask2 former and YOLO seg. The correlation is exceptionally high, with a Spearman value of negative 0.98. Next, the middle chart shows that evaluating on just 200 images captures this trend perfectly, confirming that the method is both accurate and stable with very little data. Alright, Figure 9 extends the validation-free concept to generative diffusion models on SciFar 10. The chart tracks the training trajectory over 5,000 steps. The blue solid line represents the head gradient norm, while the orange dashed line tracks the probe's mean squared error. Notice how they co-vary. As the error drops, the gradient signal generally follows, effectively monitoring training progress. This confirms the proxy remains valid, even when the objective shifts from classification to a denoising regression loss. Wrapping up, the central takeaway is that the geometry of the loss landscape serves as a powerful proxy for generalization. By tracking the gradient norm of the classifier head, this method allows for precise checkpoint selection without any validation data. This has huge implications for training efficiency, particularly in privacy-sensitive or resource-constrained environments. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.